Good morning. We are finally at chapter 13, our last week, week 8, for this course, programming language. I really appreciate everybody to join this course and work hard on this course so far. And I hope you enjoy this course. And if you have any question, just let me know. I'll try my best to help you. And in this chapter, we are on this concurrent programming. And concurrent programming is a very important topic because it is the most dominating programming paradigm in our modern programming era. And concurrent programming is strongly associated with the operation system and also our current programming language that support the object-oriented programming. So let's get started. Lecture 1 will be on background and the motivation for concurrent programming. Parallelism. The reason why we have the concurrent programming is that we want to take advantage of the highest level of the parallelism. And there are several different ways of doing parallel programming, including the vector processing, that's in the operator or operation level, or loop level. We try to branch out each iteration or each operation so that those iterations can be run parallelly. That we call it vector parallelization. Some processing engine might have a historic array to help the processing the vectors, and that would help a lot in terms of performance and can reduce the execution time greatly. Because a lot of numerical computation actually is metric based or the vector based, while our CPU a lot of time is only dealing with the scalar data. So vectorized parallelism will help a lot in terms of the performance of the system. But because of the nature of the vector processing, many instruction level parallelism cannot be parallelized in the vectors way. So we have the vector parallelism, we have instruction level parallelism, and instruction level parallelism is focused on the pipelining superscalar, those type of the operations. And then we can have the loop level parallelism. We can do loop unrolling and several techniques to help the processing of the loops. And this actually very similar to vector processing in some way, but they are different. The vector processing at the operation level actually is dealing with the single operation like add or multiply. And loop level parallelism usually is to deal with the loop level iteration that may contain hundreds of the same operations or instructions or statements in the loop. But these different loops may not be easily vectorized. It's not like metric operations only. So loop level parallelism actually is to assign a certain iteration into a processor, and so that we can actually utilize the multi-processors environment in a parallel way. So we can boost up the performance. And the next level is the task level parallelism, or we call it multi-threading or multi-processing, to utilize the multi-threaded environment and the multi-core environment so that we can boost up the performance of our program. And parallelism at task level is the main topic that we will be focused on in this chapter 13. And above that, we also have the program level parallelism. For example, the distributed computing, message passing, those type of the parallelism, and actually is among the programs, not only the process or task level. Topic in concurrent programming, we have these different topics, and we have different way of the multi-threading or multi-programming. The first one is the hardware and the memory model. We need to maintain the coherence among the processes. That is a computer architectural problem. And then second, we have the thread management, process management, and program management. This is about the programming language and operation system. Third one, we have the data synchronization. This can be a language construct or the operation systems problem. The next one is performance optimization, is the utilization of the parallelism. That actually, how can you optimize your process to boost up the performance of that task? And the last topic would be the race or deadlock issues, so that the concurrent programming can run smoothly. So our programming paradigm, starting from single threading to multi-threading, and single threading and multi-threading can share one CPU and run it. So multi-threading sometimes also called time-slice processing. But multi-processing can also be run in multi-core environment or multi-processor environment. Single-threaded can only run on single processor. And then we may have multi-processing, and multi-processing by definition will need multiple processor. And multi-threading can be multi-processor or single processor. And the highest level would be multi-programming. That means several programs running together, not just the processes. And multi-programming can run actually also on single processor or multiprocessor. And usually multiprocessor is better because one program is hard to, and many programs is very hard to run on single CPU. That would create a lot of overhead. Even though it's done very early with the multi-programming, because we have the system time sharing system, many programs can share one CPU, but that's not actually the most efficient way of doing things. Background and motivation. A process of thread is potentially active execution context. So actually, we can also call it as the program image or process image. Now put your program into the memory, we call it a process. And sometimes we call it a thread. But thread and process actually still have slight difference. For example, we can call a Java virtual machine a process, and they might have several threads running on top of this process. So this can still be different. And we have the classic von Neumann store program model of computing, and actually it has single thread control. So each thread can be a von Neumann model of computing. And multi-thread actually is trying to coordinate these different threads can be running together so that they can maintain the data coherence among them. And parallel program may have more than one thread or one single flow of the von Neumann machine. A processor can be sort of an abstraction of a physical processor. Background and motivation, multi-threading, multi-programming, distributed computing. Process thread came from multiple CPU or single CPU, of course. Kernel level multiplexing of a single physical machine. So this is a single processor. So multiprocessor or single processor can all perform multi-threading, multi-programming, and distributed computing. And these three terms are different. Language or library level multiplexing of kernel level abstraction. So these are the processor threads that can come from multiple processor or a single processor with the kernel level multiplexing, or language or library level multiprocessing of a kernel level abstraction. And kernel level multiprocessing of the single physical machine is the multi-process. So you run multiple processes in the machine. And then library and language level multiprocessing of kernel level abstraction. That means I have a process that is similar to Java virtual machine, and we have the different thread on top of it. So these three all called multi-threading on a or multi-threading is the last two, and this first one is multi-processing. And we can also have the multi-threading on this multi-processing or multiple CPU. So they can run in true parallelism, unpredictably interleave, or run until block. So these are three different ways of implementing the multi-threading or multi-programming. So most will focus on the first two cases, which are equivalent, difficult to deal with. And the last one doesn't make sense in a lot of situations because your CPU may be occupied by certain process. So most of the multi-threading environment is running in true parallelism with multiple CPU or unpredictably interleave with this kernel level multiprocessing of a single physical machine. And if you are in the language level like Java, you can be running the third case. Background and motivation. Two main classes of the programming notion: synchronized access to shared memory, message passing between processes that doesn't share memory. Both approaches can be implemented on hardware design. For the other, low shared memory and message passing hardware tend to be slow. So there are two ways of implementing the multi-threading or multi-programming. First one is synchronized access to shared memory. And this one actually is the majority of the things being done for multi-threading. And that's the main topic we will be discussing. So that multiple processes share the same memory, and this memory can be updated by each of them, each of the process. So we need to handle the data coherence among these two processes. And parallelism can also be achieved by message passing between processes that don't share memory. So each one is a single process or single program, and then you pass the message around them. This is called message passing. And both of them, for this synchronized access to share memory or message passing, both of them are very important. So both approaches can be implemented by hardware designed for each other. Low share memory and message passing hardware tend to be slow. Right here, I told you the level of abstractions. We have instruction, method, task, program, and system. And different levels have different way of doing parallelism. And in C# current environment, we had a parallel classes, and we have a task parallelism. And these are called parallel FX. And it is the way that C# doing the parallelism. And we have a task parallel library. Actually, this is used in many languages. We have the GUI thread, module agent, and then we have this task parallel library. So this different program can be called in this library and then have the workers thread to help running it. And we have the .NET environment, and that has this .NET language integrated query. The language integrated query link is the breadbox parallel library, and it can be done for several things. Can have the object, dataset, SQL, entitles, and XML. And one thing that we need to handle is the rest condition. A rest condition occurs when actions in two processes are not synchronized. and program behavior depend on the order of which the action happens. Race conditions are not all bad. Sometimes any of the possible program outcomes are okay. So for example, we have this program right here, and then we actually have this function foo, and we have this return value equals n-1, and then if actually this is a multi-process function, so actually if it is 0, it keep dropping the this n. If it drop to 0, then we increase the count for 0. So we actually fork out several threads with the initial n, and then we actually running this foo function in parallel with multi-processing environment. So each of the process actually run this RTN update and the checking for RTN equals 0 program. And we have a thread 1 starting from here, and thread 2 starting from here. And these two threads can go into the rest condition. Because this 0 count is shared by all the function foo. So right here, actually, we update this R1. Actually, we want to update the 0 count, but we assign R1 this memory value 0 count. We load it to register 1, and register 1 increase self and write back to the memory. But during the process, we have the thread 2 to compete for the resource of the R1. So it may update during this one. It may actually set this R1 to 0 count. So actually, while this one is updating the R1, this R1 have been read out for R2. For thread 2. So this will create trouble. So if the instruction interleave roughly as shown, both threads may load the same value of the 0 count, because at the time R1 is loaded, they have the same value. So actually this one should wait for this to finish. Otherwise, this update had not been finished, but it read the same data, and then they perform the same thing. They set the same value to 0 count. Instead, we want this thread 2 to be after the thread 1's update for 0 count. That is a better way of setting it. So if the instruction interleave roughly as shown, both threads may load the same value of the 0 count. Both may increment it by 1, and both may store the only one greater value back to the 0 count. The result may be 1 less than what we expected. So actually, this is wrong. We need to have some way of handling this. And that's one of the topic we talk about for data synchronization. And otherwise, such function foo cannot be parallelized. So rest condition, we want to avoid rest condition. Suppose processor A and B share memory, and both trying to increment X at more or less the same time. That will create trouble. And we need to have some sort of mutual exclusive access to certain data in order to make it work. Very few processors support arithmetic operation on memory. So each processor is queued such a thing. Suppose X is initialized to 0. If both processors execute these instructions simultaneously, what are the possible outcomes? So, and actually it could go up by 1 or by 2. That is what we actually seen in the previous example. So data synchronization is very important. Synchronization is the act of ensuring what events in different processes happen in the desired order. Synchronization can be used to eliminate rest conditions. In our example, we need to synchronize the increment operation to enforce mutual exclusion. So mutual exclusion is the key for performing data synchronization. Most synchronization can be regarded as either mutual exclusion or condition synchronization. And these two actually are the main topic for concurrent processing. Mutual exclusion, making sure that only one process is executing a critical section or critical region, touching a variable, for example, at a time. Condition synchronization, which means make sure that a given process does not proceed until some condition holds. So actually, this is also a type of synchronization by control. Mutual exclusion is the synchronization for the memory or system state. But synchronized by condition synchronization is for the control of the program. So right here, I show you an example of the critical section, or we call it atomic code block. So we can use three different ways. The first way is called lock-unlock mechanism. So in my program, when I enter into a certain critical section, I set the lock to be locked. So other people cannot go into the same critical section, and I release it until I finish. This is called lock and unlock. The other way is called wait and signal. So when I want to go into a critical section, if there is somebody already in there, I will wait until he finishes, he signal me, and then I go into critical section. But when I go into a critical section, all of the other process or thread will be stopped from getting into this critical section until I signal everybody to wake up to compute for the CPU. The third way to implement the mutual exclusion is using the semaphore. And semaphore is a wait list, but with a certain number of seats. So when I go into the check for semaphore, if there doesn't have enough seat, then I will wait on the semaphore. Same thing for B. And if there is an empty seat, then I will go into the critical section. And when I finish, I will release my seat and then notify all of the other processes that are waiting on the same semaphore. So these are three schemes for mutual exclusion. We also have condition variable, monitor, critical condition region, and software transactional memory. So these are different topics we will touch in this chapter. One might be tempted to think of mutual exclusion as a form of condition synchronization. The condition being that nobody else in the critical section, but it isn't. It is called the data synchronization for the critical section. And condition synchronization is a different thing. The distinction is basically essential or universal qualification. Mutual exclusion requires multiprocessor consensus. We do not, in general, want to over-synchronize, not eliminate parallelism, which we are generally want to encourage for performance. So we don't want to over-synchronize for setting up a lot of mutual exclusion region. Then if there is too many mutual exclusion, then the parallelism will drop for the program. Basically, we want to eliminate bad race condition. For example, the one that caused the program to give incorrect result. To implement synchronization, you have to have something that is atomic. Atomic that means that you have to finish it before we move on to the next session, and it cannot be interrupted. That means it happens all at once as a indivisible action. In most machines, read and write of individual memory locations are atomic. In early machines, read and write of individual memory locations were all that are atomic. To simplify the implementation of mutual exclusion, hardware designer in the cities to build so-called read, modify, write, fetch, and find instruction into their machines. Lecture 2, Multi-threaded Programs. Coroutine. We saw this coroutine in chapter 9. Coroutines are computer programs component that generalize subroutines for non-preemptive multitasking. By allowing multiple entry points for suspending and resuming execution at certain locations, coroutines are well suited for implementing more familiar program components such as cooperative tasks, exceptions, event loops, iterators, infinite lists, and pipes. So coroutine is a way to implement several programming structures. Producer-consumer model. We have two coroutines, coroutine produce and coroutine consumer. These are very important. This happens very often in our concurrent programming case. For example, the bounded buffer, but right here we have a queue example. So this queue, actually, if it is not empty, you can continue to produce your elements and add to it. And you will wait, and if it is empty, and if it is not full, and if it is full, I'm sorry, then you would wait for the consumer to consume, because when it is full, you can no longer add things into it. And for the consumer side, if it is not empty, then you continue to consume. Until it is empty, you can no longer consume, then you will yield to producer to produce. So these two can happen at the same time. And sometimes you can produce and you can also consume if it is not full and not empty. But once it is full, then you can no longer produce. You will wait until the consumer consume. And on the other hand, if you are empty, then you have to wait until the producer produce. Otherwise, you cannot consume. So this achieves time-shared concurrency in centralized or distributed environment. So right here we have a chart where coroutine A, we run to a certain point, we start coroutine B, and then we to a certain point and we go to C, something like that. This flow is the transfer of controls. So the idea is A program may run to a certain point and got interrupted by B, and then B by C, and C will be by A, and A continue from where it lost control, and then it will resume and being interrupted by B, and B by C, and then C by A, and A continue. From A's point of view, actually it is running at the time-share format, and for B sensing and D for sensing. And in real-time domain chart, it will be something like this. You have one main program running, and then coroutine 1 running, and go back to main, and go to 2, and then come back, something like that. This is the time domain chart, and this is from program flow chart. So this producer-consumer model is very good for discrete event simulation for concurrency. And for you to write a program like this for simulation, it's not really hard. You can actually use a counter as the timestamp, and then you can write certain events or some model. When you run to a certain function or coroutine, you advance the counter, something like that, and you can actually create a discrete event simulation environment for that. Coroutine for asynchronous control flow. It is for web-based application, event loop, exception, cooperative task, and etc. In Python, you have several coroutines threads, and one thread may have several coroutines, and the other thread can also have many coroutines. And actually, in the web environment, you can have the request from the internet, and then your main thread is over here, and this main thread is person. It will ask to access the database, and then the database will come back. The person will make another database to access the email. Email will come back, and then you will access the API and will come back, something like that. So web environment can also be considered as a coroutine environment with asynchronous control flow. Web browser parser. Web browser parser, as I mentioned, the JavaScript is actually using the event loop, and event loop can be think of as a dispatcher. A dispatcher itself is a control for the coroutine. So right here, let's look at this. String-based code from hypothetical web browser. The first approximation, the parser page subroutine is the root of a recursive descent parser for HTML. So the web-based browser parser itself is a recursive descent parser, and we need to run that program in a time-shared environment. And it actually is a serial program, but we want to mimic it as a time-shared environment for concurrent programming. In several cases, however, the action associated with the recognition of a construct, background image table, or for frame set proceed concurrently with continuous parsing of the page itself. What does this mean? This means that you actually want to load your background image or table or frame. At the same time, you continue to parse your page. So you won't hold up for certain images. So sometimes your image download is slower than your page download. I'm sorry. Your download of the web page maybe is at the same time with the download of your image. In this example, concurrent threads are created with the fork operation. An additional thread would like to execute in response to keyboard and mouse event. So right here, we have this parser program. We have parser HTML header, and then we try to get in some token. So some simple program, you just try to match it. And some more complicated token, you actually see a background, then you start to fork a render background. You try to download the background from the program. So same thing for image. And once this fork out, there is a process to keep running, and images fork out, you have a download for images running. You can continue to pass some other stuff. This is the idea of the multi-threading for web-based web browser parser. But remember that the event loop for this is actually serial. So the parser program is using the serial execution flow to mimic the concurrent programming for these parsers. So sometimes the image will take longer time, but your program won't be blocked by it. Dispatch loop alternative. And dispatch loop browser data structure associated with the dispatcher loop keep track of all the tasks the browser has yet to complete. It must identify the various subtasks of the page, image, table, frame, so that we can find them all and reclaim their state if the user clicks a stop button. To guarantee good iterative response, we must make sure that no sub-action or continued task take very long to execute. The principal problem of the dispatch loop, beyond the complexity of subdividing tasks and saving state, is that it hides the algorithmic structure of the program. So basically, the dispatch loop will break down the whole program, and it is hard for you to see how the program is structured. Even distinct tasks could be described elegantly with standard control flow mechanism, if not for the fact that we must return to the top of the dispatch loop at every delay-induced operation. In fact, the dispatch loop turns the program inside, make the management of tasks explicit, the control flow within task implicit. What does this mean? This means you have a dispatch loop. Your execution is serial. So you actually will dispatch several threads and let it running. And at the same time, you will hold up some long waiting process or task for a longer time. And then it will come back at the later time for serial downloading. And if you are in a pure multi-threaded environment, this won't be a problem. The resulting complexity is similar to what we encounter when trying to enumerate a recursive set with iterator object in section 6.5.3. Only worse. Like Chou iterator, a thread package turns the program right side up, making the management of tasks implicit and the control flow within threads implicit. So this is the dispatch loop alternative. You actually have the dispatch queue for several items that we call it events that need to be executed. So you will go to check next number, and then you run it, and then after you finish, you jump to another task. So actually, your dispatch loop will have a busy loop, try to do something input driven. If there's a new event, then we will do the following things. If the existing task is waiting for E, we continue. Else, if E can be handled quickly, then we do so. Otherwise, allocate and initiate a new task and continue that one. So we actually let it go, and then if it hold up, we will stop another easy one go through, and otherwise we will keep poking a certain task, run it, and then return to some other task. And that's the way we have this dispatch loop alternative. And compared to the previous one, this one actually can be run by dispatch loop, but if you implement the fork correctly, but if it is not using the dispatch loop, this will be demanding a certain execution in a multi-threading environment. So dispatch loop is an alternative to the true multi-threading environment. And look at this continue task. If it is in rendering the image, then E is a message containing the next block of data, and then we continue image render. But actually, this means we put something into a queue, waiting for the execution. And for the multi-threaded environment, we need to make sure that if it is in shared memory environment, we need to make sure the processing is coherent in their memory model. So memory coherence in concurrent environment is very important. Say right here, we have multiple processors. We have cache of different processor associated with the processor. And then we have a common bus. And then we have main memory over here. But say we have a variable X, and then we need to make it consistent that the local copy of the cache, the data X, when access the processor, they will get the right copy. But sometimes we doesn't write it back to the memory directly, then their value will be different. So there are several protocols to maintain the cache coherence problem for shared memory processor. Here, processor A and B are both read variable X from memory, so they take two copies. As the side effect, a copy of X has been created for the cache of each processor. If A change X to 4, A change it to 4, and B read it again, how do we ensure that the result of 4 and not still cache the 3 will be accessed by B, and Z read X into its cache? How do we ensure that it attends 4 from A cache instead of 3 from main memory? So that's the problem we have. So there are several protocols. If the data already in the cache, we have no right and write invalidate cache go directly to the memory. So one way is use write invalidate. That means if you want to write A, or we want to write 4, and they already one variable in B processor, so we write A, and at the same time we invalidate this copy. So there is nothing like that in this. There is no X in B anymore, and we can write A, and then later we let it update to the memory. Let's look at how it works. So we have write through. Write through is one protocol that when we write directly go to the memory and cache. So write through scheme actually is when we want to write 4 on the A processor's cache, then we directly update the memory. And then when Z requests for it or B requests for it, we will update from memory to cache. That's called write through. When you write through to memory. And write back actually CPU write only once, CPU only write to cache. Cache write to memory later when block is evict. Wait until we kick the block out of cache. We call it write back policy. How does this work? Actually, we only write to cache. And then only when this is to be switched, for example, like you have a context switch, then you actually write to the memory. That's called write back. But write back will need some extra mechanism to make sure the cache coherence. Now, let's look at this through P bus. Through P is picking. This through P cache coherence protocol. Write update, write invalidate, and write back. So right here we have several processors, and we have several copies of the same X data. And to write through, we just have this processor write 100 into the memory. That's it. That's called write through. And then we can actually, at the same time, we need to update the copy on this first processor. That's we need to write update. So this one here is write. This one is write through. This is one write update. So write back, when you write to here, you can also invoke write update, either at the same time or later. That's called write update. So write update is to update other people's copy. And another term called write invalidate. Write invalidate means when I write this, I invalidate this 505 copy. And even though there's a memory and in the cache difference, but actually later we can update the memory by write back scheme until it got context switch, because there is no copy of this being with the X value, so you can write back later. But if some process request, then you have to write through first and allow the other cache to fetch it. So there are certain different kind of protocol. So right here we have the write update through P bus protocol. This is one of the example. When CPU A read X, then our bus activity is cache miss for X. When there is a cache miss for X, you will have to read it from memory. Then content of the cache A will be not existing. The memory location X is 0, then you should get 0 as well. And then if B read X, cache miss for X in B, B's cache will be missing. And A's will get 0, B will also get 0. The X location should also get 0. And when CPU A write a 1 to X, then we write broadcast 1. Write broadcast actually is write through everyone, and can include in your own location and other cache and memory. This is called write broadcast. And when B read X, you will read this one. So write broadcast is another term to write and broadcast to other caches. And whether you use write broadcast, write update, write event date, or write back, it all depends on how you design the bus and when should you maintain the data coherence in the right way. And actually, this requires a whole chapter in microprocessor design for this whole different terms. But the key point is we need to have a cache coherent protocol to make sure that the shared memory will be valid. And actually, nowadays, memory protocol is not easy and not only single protocol can implement it. Concurrent programming, fundamental part 1, languages. We'll talk about the languages that support the concurrent programming. Language and libraries, widely used parallel programming systems. For language, we have Java and C#. These are typical shared memory programming language. Extension, we have open, message passing system. Open multi-threading program. We have open MP extension. In library, we have the Linux pthread, Windows 32 thread. And message passing, we have MPI, message passing interface. That's the library, or we call it API. And for distributed computing, distributed means your computer are at different locations. Multiprocessing means you have multi-programming environment. Shared memory, you have multiple process or task or thread, but you share memory. So in terms of locality, distributed environment is more spread. Message passing is in between. Shared memory is more centralized. And distributed environment, you have remote procedure code, internet libraries. There is also a very large amount of experimental, pedagogical, or niche protocols, or niche proposals for each of the regions in the table, including regions where no system is currently widely used. Languages. For shared memory languages that support this concurrent programming, actually we have Java, C#, C++, Rust, Scala, and Haskell. For message passing, we have Go language. For distributed system, we have Erlang. And the package extension, we have OpenMP. And distributed system, we have remote procedure code in operation systems. And for the library, we have Qt, pthread, .NET environment that support the shared memory. And then message passing, we have message passing interface. And the distributed system, we need this SymGrid. Thread creation syntax. Almost every concurrent system allows threads to be created dynamically. Syntactic, semantic details vary considerably from one language to from one language or library to another, but most conform to one of 6 principal options. Code begin. So these are the program syntax for language syntax for these different package or extensions or libraries. You have code begin, parallel loop, launch at elaboration. Elaboration is declaration, fork, implicit receipt, early reply. So these are different program structures. We will probably touch some of these. The first 2 options delimit thread with special control flow construct. The others using syntax resembling or identical to subroutines. So actually, these different ones are similar to subroutines for the last 4. Here, let's look at the C++ code begin. And here is the pseudocode. And right here, we have the poking statement 1, 2 to n. Actually, we list down here that these different statements will be branched out at the same time. And in C++, we have a pragma, and this pragma actually need to call this open MP. MP probably means the multi-threading programming. And sometimes this is very confusing, you know. In the previous one, we have this message passing interface. And message passing and multi-threading programming, actually, they share the same shell name. So C OpenMP directive using the pragma, and you assign this whole pragma is actually OpenMP package. All begin with the pragma OpenMP. The punch sign must appear in the column. Most directive, like those shown here, must appear immediately before a loop construct or a compound statement delimit with the curly braces. So actually, you need to have this over there, and then you have curly braces. So this whole section is a section. These are sections for OpenMP. And then right here, something you put these braces is run in the OpenMP section. So these two will be branched out at the same time. If we under a sections, and one section is one branch. Thread creation syntax, parallel loop. Parallel loop, we use a C# parallel FX library. So this is a 4, but it's actually is a parallel version. So you start from 0 to less than 3, and then you actually run I. Now I will be parallel. It actually will be increasing every time. And then you actually write out the information. Thread I is here. And for C++ version, you have this parallel 4 as defined in OpenMP. And then you actually write just like you are writing normal for loop, but it will be forked out as parallel for loop. Many concurrent systems, including OpenMP, several dialects of Fortran, and the recently announced parallel FX library for .NET provide a loop whose iterations are to be executed concurrently. In OpenMP for C, we might say like this. So here are the C# for parallel FX library, and the C with OpenMP extension, and Fortran 95 would be written down like this. And it's for all. And this is also concurrent programming. And as you can see right here, we have another parallel loop, C with reduction in OpenMP. And as I mentioned, not this one, sorry. Not this one, sorry. Right here. Actually, the for loop, parallel for loop is using the loop unrolling technique. So we unroll the loop so that each iteration can be run in parallel, but that actually is not real multi-threading programming. It's not task level, it's just loop level loop unrolling. And that loop unrolling can be running in parallel. So each time one loop being one iteration being run. So optional clauses on parallel derivative can specify how many threads to create, which iterations of the loop perform in which thread. They can also specify which program variables should be shared by all threads. Why this is needed? Because when we do this parallel processing, say for this C program, we will open P, parallel for, schedule static, default shared, reduction plus sum. And actually we try to parallelize this. But because we have limited resource, so we need to indicate that the compiler should divide the iteration among the thread. And maybe you have only 3 threads, but you have 100 iteration. So you cannot run 100 iteration fully parallel at the same time. Instead, you will be dividing the iterations among the threads in contiguous group. And then you finish like 3 iteration at one time, and then you sum their data up using the reduction plus signs, the sum. Default share clause indicate that all variables other than I should be shared by all threads. So I is not shared. Other parameters are shared. Reduce sum clause makes sum an exception. Every thread should have its own copy, and the copies should be combined with plus at the end. So they can also specify the program variable should be shared by all threads, and which should be split into separate copy for each thread. It is even possible to specify that private variable should be reduced across all threads at the end of the loop using the commutative operator to sum the element of a very large vector. For example, one might write the following like this: is a sum of big vectors. Launch at the elaboration. Elaborated task in parallel. Elaborated means declared. So actually, you can do it by declaration. So multi-threading can be done by parallel loops, can be done by declaration of the task, can also be done by parallel loop in the library. And code begin end in different language. So these are different program structure that we are talking about. Now let's look at this declaration. In several languages, Ada among them, the code for a thread may be declared with syntax resembling that of a subroutine with no parameter. And when the declaration is elaborated, a thread is created to execute the code. In Ada, we may write it. So a procedure, we define a task, and this task will be a branch. So when you declare this, actually, if P is called, you have a side task going on, and a P will go on, and then there is a merge point. Actually, is the end of the join point. Task T begin to execute as soon as control enter into P procedure. If P is recursive, there may be many instances of T at the same time. The main program behaves like an initial default task. When control reaches the end of the procedure P, it will wait for the appropriate instance of T to complete before and return it. So this elaborated task in Ada is quite simple. You declare it, and then you will run as a branch for different threads, and then later they will join. Now, the next thing is the fork and join. Fork and join are implemented in several languages. In Java, one obtains a thread by constructing an object of some class derived from a predefined class called thread. And then the thread can have the, actually it will be a fork. So image render extends thread. Thread is a manager for the task. And then over there, thread actually implement the runnable interface. And runnable interface, you can put your code to be run by this thread over here. And this one is image render. You have its own constructor. So actually, this constructor is preparing the environment for the run function to run. So first, when you construct a image render with this parameter, you actually build a image render thread, but it is not, the thread is not started yet. You will prepare for the data in the thread before you run. And once you want to run this parallel version, then actually you should have render.start. Once you call this render.start, actually in Java, this run function will be run. And because this is the runnable interface that been inherited by the thread class. So start make the thread runnable, arrange for it to execute its run method and return to its caller. The programmer must define an appropriate run method in every class derived from thread. The run method is meant to be called only by start. The programmer should not call it directly, nor should they redefine start. There is also a join method that actually will finish it. Once you start and you finish the run, you will run this run.join. The constructor for a Java thread is typically save its argument and field that are later accessed by run. So here, actually, you set up the environment. That's what this says. In effect, the class derived from thread function as a object closure. So lifetime of thread. Number A, actually this A is thread always properly nested with fork join. I'm sorry, A is with call begin parallel loop and launch and the elaboration. Actually, you have run it parallel, and then you run it parallel if it is nested. This is a parallel loop, launch at elaboration or call begin. For fork and join, you run to here start, you will start some thread, and then right here start, you will run some thread and join. And right here, you continue, run and start. Thread creation syntax. There's another way to do it called implicit receipt. We have assumed that all our examples so far that newly created thread will run at the address space of the creator. In remote procedure call system, it is often desirable to create a new thread automatically in response to an incoming request from some other address space, rather than have a existing thread executing a received operation. A server can bind communication channel to a local thread body or subroutine. What is happening is like we have a client server computing model. Actually, this is distributed, and we are running in the remote procedure code. So the client requests a message from server. So the server, there is a implicit receiver that will run it. And the next one, you will do the same thing. So this one, the responding side is called the implicit receive, and it will fork a different process or thread by the server. But the server itself may have something listening the client to issue the request. But once the request arrives, it will branch out a different thread other than this server's main thread. So when the request comes in, a new thread springs into the existence to handle it. In effect, the bind operation grants the client the ability to fork within the server's address space. So once it actually initiate, the bind operation will let this call being controlled by the client. Through the process is often less than fully automatic. Early reply, modeling subroutine with fork join. We now think of sequential subroutines in terms of a single thread, which saves its current context, execute the subroutine, and return to what it is doing before. The effect is the same. However, if we have two threads, one that executes the caller and another that executes the callee, in this case, the call is essentially fork join pair. The caller waits for the callee to terminate before continuing its execution. Nothing dictates, however, that the caller had to terminate in order to release the callee. Nothing dictates that, however, that the callee had to terminate in order to release the caller. All it really had to do is complete a portion of its work on which result parameter depends. So actually, this is a modeling of the subroutine with fork join, and this one actually will happen in a lot of also the distributed environment. In the previous lecture, we talked about several different programming structure for concurrent programming. Let's go back to that. We had these different ways to create a syntax for different languages to create a concurrent programming feature. And in this lecture, we'll be talking about the implementation issue for these different structures. So first, let's look at the multi-threading. We are mainly focused on task level parallelism. So for data parallelism, we have the input data, and then we put into several tasks, and then we run it, and then we sum it up. This is just like a for loop. We put different I and the data in there. We perform different tasks. At the end, we sum it up. It's called vector processing. And this vector processing can be done at the loop level using loop unrolling, and it is possible. You can also use the systolic array or parallel processing vector processing unit in your CPU. That is actually much faster. So that's what we mentioned. Very early, we have a vector parallelism. If we use that in the operator level or loop level, that actually this is not loop level, it's the operator level, and we unroll the loop into the vector format. And actually, if the each statement is uniform, and we can actually using the vector processing unit to help you to solve the problem instead of loop unrolling. But loop unrolling is also available if you have a for loop structure, as we mentioned in the previous lecture. But now we are talking about task level parallelism, multi-threading. So task level parallelism, actually, you have input data, but you branch out into different tasks. And then each of the tasks may perform differently. And then at the end, we sum it up at one certain aggregation task. This we call it multi-threading instead of the vector processing. These two are different, but sometimes you can also call this different task as multi-threading. It's also okay to call that. So I should say multi-threading is a more general term compared to the vector processing. And vector processing is one way of the multi-threading. And multi-threading may handle tasks of different type. Vector processing can be same type, can be put into the operators in the instruction level. And here is the two-level implementation of thread. Basically, in your user space or language level, you have several threads. And these different threads will be served by different processes in the OS level. So there's one scheduler needed from thread scheduler, and then there's another process scheduler in the OS level. So this is called two-level implementation of thread. But there is also possible that you use only the OS scheduler for one level for a certain language. So it actually depends on the compiler and the language. And the thread scheduler implemented in library or language runtime package. Multiplexing thread on top of one or more kernel level processes. Just as the process scheduler implemented in the OS kernel, multiplexed process on top of one or more physical core. So there are two levels. the thread on top of process and process on top of CPU core. And then in Java, we have the default thread. We have main program, we have garbage collection, we have event dispenser, we have timer, and we can have some daemon process. These are all existing default default thread in Java environment. And right here show you the OS process scheduler. We may have several processes. Each process may contain several threads, and thread will have the Java content. I will call or some program content. I'll show you later. But this actually will have the thread scheduler. Actually, it should be called process scheduler. And sometimes actually, if you break down a thread to each process, so it can also be called thread scheduler. So this actually heavily depends on one level implementation of the thread, or two or multiple level of the implementation of thread. And that thread scheduler or process scheduler will handle the processes in the OS level. Java memory model, as we mentioned, each thread has its own thread image. You have thread stack and heap. And heap is the general copy. But in your program, in your computer system, the heap will be staying in the RAM or main memory, and your thread stack can be in your CPU, can be in your memory, and can be your main memory. Same thing for the heap. When you do programming, they can exist in different locations. And then your program or the CPU need to be able to adjust to the right copy. And that also related to the cache coherence problem. So for each thread, we have program counter, Java virtual machine stack, frame, call frames, that is actually in the stack, local variable array, operand stack, dynamic linking table, native method stack. So they are a lot of information in your thread image. And thread image is only one part of your Java virtual machine memory. And there are some other things like method area, heap area, or something like that. But for each thread, you need to keep track of these things in the thread image. Concurrent programming fundamentals. Scheduler gives us the ability to put thread process to sleep and run something else on its process or processor. Start with coroutine. Make unit processor run until block thread. Add preemption, prioritize, and add processor. So these are different stages to implement the scheduler. We start with the coroutines, and then make unit processor run until block thread. And then we try to do preemptive instead of run until blocks. And then later we add more processors. So the state diagram for OS thread will be like this. You can new and then go to the ready state. And ready, if a process or task is ready, it has the right to be scheduled for running. So when it is dispatched, you run it. And if there's an IO block or timeout, or you have some user-defined sleep, you go into the wait state. And wait state may be because of some reason you cancel it, then you would go into terminate state. Or otherwise, you will go back to ready. Once the blocking issue is done, it is cleared, then you go back to ready and got dispatched to run again. And actually, your scheduler may sometimes kick out of the running process to make sure that it's preemptive, and actually you will go back to ready state to compete for the CPU service. So to implement it, we have a thread, current thread that's running, and then we will keep a ready list. And this ready list for head and tail, you can run a round robin format that's circular queue, or this linked list with. So the first one is higher priority, the later one is a lower priority. So that's the ready state. And then we can also put the process into a wait state or wait for condition bar. Wait for condition, we have the wait on time, wait on event, and block IO. These are the data structures for a simple scheduler. A denied date current head is running, this one is running. Thread on the ready list are runnable, these are ready to be run. Once the guy got kicked out, one of the highest priority will be going in to get serviced by CPU. If a thread on top of more than one OS process, each such sub-process will have its own current thread variable. If a thread makes a call into the operation system, its process may block the kernel. Uniprocessor scheduling. At any time, a thread is either runnable or block. Runnable ready or block wait. A runnable thread is running in the ready queue as a runnable and ready. A queue is prioritized. Sometimes we use a round robin. This would be round, R-O-U-N-D, round robin, if the same priority. To yield the processor to another thread, run reschedule. So reschedule is to yield your processor so actually this will perform the preemptive scheduling. If time expires or block, a thread can yield to the processor to the other thread and return to queue. So that's actually is right here from your running, go to wait, and then go back to queue, the ready state. To enter into wait state, run sleep on. This is run sleep on time. This is one of the way to stop. The other one is event or exception handling, can call it. Cooperative multi-threading, long-running thread must yield at certain point to be fair. So here we have a reschedule. We will dequeue from the ready queue and then get a thread and transfer to the last thread for running. So this one actually is from here we dequeue this one and get it into the running thread. And we have yield for the actually we enqueue the current thread, put that into the ready list, and then actually we can put a certain queue of head to current thread into a certain queue, put that into queue for sleep on. So this one actually is putting this guy into a wait for condition or wait some other wait. That's actually wait on time. You can have the wait on time queue. Concurrent programming fundamental preemption. Using timer interrupt in OS or signal to trigger involuntary yield. So actually the guy running don't want to give up, but we need to wake him up and yield its control on the CPU. Require that we protect the schedule data structure. In yield, we need to disable signal, enqueue the current head into the ready list, do rescheduling, and we enable signal. So during your yield process, you need to disable the signals. Note that reschedule will take us to different threads, possibly in code other than yield environment. Early call to reschedule must be made when signal disabled and must re-enable them upon its return. Multiprocessor scheduling, we can extend our preemptive thread package to run on top of more than one OS provided process by arranging by sharing the ready list and the related data structure. More than one thread will be able to run at once. In a single thread processor, the program will be able to make forward progress even when all but one of the processes are blocked in the operation system. Any thread that is runnable is placed in the ready list. When a process call reschedule, the queue-based ready list will give it the longest wait time. We call it the round-robin algorithm. The ready list of a scheduler might give priority to iterative or time-critical threads, or to a thread that last run on the current processor and may therefore have the data in the cache. So these are different way of scheduling based on the algorithm round robin or the last run on processor. Keep your cache hard. There's several different algorithms for priority write. Chou and cross-site parallelism introduce races between code in separate operating system processes. To resolve the races, we must implement additional synchronization to make sure scheduling operations in separate processes atomic. Now we will start the lecture 5, the synchronization scheme, the data synchronization scheme. Part 1, we will be on lock and barrier. And before we dive into the lock and barrier, let's look at the implementation method for synchronization, like including disable interrupts, bakery algorithm, spin lock, and barrier, and sophomore. And conditional critical regions, or sometimes the critical region is called critical section. And then the condition variable and conditional critical section region also called CCR, and condition variable also called CV, and then monitor. And up to from speed lock to semaphore, these three, we call it data synchronization scheme. So actually, it's a general idea supported by different languages. And then these CCR, CV, and monitors, they are more like a program module or program concept that will be some implemented by some language, but may not be available for several other languages. So now let's introduce the idea of critical section. The critical section protocol is like when we try to access some shared memory location, and we don't want other people to get in, so we will have add a entry section. So we lock it, or we do some barrier to not allowing other people to get into the critical section. Until I exit it, then I allow other people to get in. So that's called critical section. A critical section protocol consists of two parts: an entry section part and exit section part. And between them is the critical section that must run in a mutual exclusive way. So I have a exclusive access to this critical section, and any other process cannot enter into this critical section. Implementing synchronization. Condition synchronization with atomic read and write is easy. So atomic means complete and have the mutual exclusive access. You just cast each condition in the form of location X contain Y, and you keep reading X in a loop until you see what you want. Mutual exclusion is harder. Much early research was devoted to figure out how to build it from simple atomic read and write. Decker is generally credited with finding the first correct solution for two processes. In the early 1960s, Dijkstra published a version that worked for N processes in 1965, and Dijkstra algorithm is very important. Peterson published a much simpler two-process solution in 1981. Implementing synchronization. Repeatedly reading a shared location until it reaches a certain value is known as spin or busy waiting. So that's one way that you wait while people are executing that is called busy waiting. A busy waiting mutual exclusion mechanism is known as a spin lock. And actually, if you think about you going to a dentist or you going to a medical doctor clinic, there's only one doctor, and the one cash service is in there, and someone outside is in a busy waiting situation. And once you go into the treatment room, meeting with the doctor, and he locked the door until he opened the door and he step out, and that actually other people in the lobby actually are in a busy wait state. The problem with the spin lock is that they waste the CPU cycles or processor cycles. Synchronization mechanisms are needed that interact with the thread process scheduler to put a processor to sleep and to run something else instead of spinning. Note that spin locks are still valuable for certain things and are widely used. In particular, it is better to spin than to sleep when the expected spin time is less than the rescheduling overhead. So spin lock sometimes is okay if the cost for control transfer is higher than waiting. Say, for example, you can, just like the dentist or doctor's situation, you can wait in the lobby. It may be pay off. Then you go home and waiting for the doctor to call you. But if there's a guy who is occupying the treatment room for 4 hours, 5 hours, then I would rather go home. So actually, there's a trade-off whether to use the busy waiting mechanism or to get the wait and signal mechanism. That actually depends on the application a lot. Now let's look at the spin lock, test and lock. The lock variable actually is your own lock. Say whether you lock the critical section or not. So it set a Boolean variable to be true and return indication of whether the variable was previously false or not. So if you try to test and set this lock, if it is false, then while not false, then it will be true, then you actually spin waiting over here. So you don't get a lock, then you actually spin waiting over here. But the problem with this test and set in the loop tend to result in unacceptable amount of communication on the multiprocessor as the cache coherence mechanism attempts to reconcile writes by multiprocessor attempting to acquire the lock. The over demand with hardware resource is known as contention, because if you are in a shared memory environment for multiprocessor, every time you try to check the memory on the cache, so you have a cache coherence problem. You need to write through, write update, write embedded, another operation. So it is not efficient to do that. And you don't acquire the lock, you will be spinning, checking that forever. So to reduce the contention, the writer of synchronization library often employ a test and set this kind of operation. You have the test and set test first, and then you try to set it. And then set a test and set lock. This is a new lock called test and set lock, which spin with the ordinary read until it appears that lock is free. So right here we have a lock. While the lock is set, you actually spinning. And before you enter into here, you make sure that is actually you test and you do not get a lock. If you do not get a lock, you actually you get into here and test on the lock condition. And if lock is actually released set it to false. Somebody set it to false. You know, when this is set, actually somebody write it, set it to be true. So you have to look at this as in the multiprocessor environment. So if somebody releases this become false, then you will jump out of this and try to test and set the lock. And if somebody say at that time lock it already, then you will not be able to test and set. You will go into the lock loop. So this, you need to think about this in the multi-process environment. The lock is actually maybe set by other people, not yourself. So if originally the lock is false, you come here and you set the lock, and you go into the internal critical section. If you come here is false, it actually is locked, and then it's set by other people, you will be locked and you cannot get in. So that is how spin lock and test and set lock and test and set lock work. Barrier. Barrier sense reversing barrier. Each thread has its own copy of local sense. Threads share a single copy of count and sense. So this is the program. The idea is the following. You have set up a barrier. Say this is actually a synchronization point, task continuation point right here. So everybody need to arrive at this point until we can start. So this is some sort of a synchronization point. This is different from the lock and critical session idea. This is called barrier. Barrier means that everybody need to gather together at this point. So before everybody arrive, other people need to wait until the last one comes. So that's the idea of barrier. So the program is right here. Initially, we have a shared copy of the memory called integer count. And that one set to the value n. So n, say in this example, n should be 5. So you set the shared sense boolean to be true. And then first thread local copy of local sense to be true. Okay. So initially, you set the local sense to be false. You reverse it. So, and then each thread will toggle its own sense. So everybody will toggle yourself. You will be toggled back later for this local sense. So we try to fetch and decrease count equals 1. And if I arrive in the barrier, then I will actually reduce the decrement this count, because I finished, I arrived already. And until the last one, if the count is already a 1, that means everybody arrived. If everybody arrived, then actually we will reset the count to n. So we reset the sync point for next barrier. And actually we update the sense, global sense, with the local sense. Allow other thread to proceed. Now actually this works as like a signal. Say I'm the last one, so I set this sense to be false, and then everybody will move on until that until that your sense is equal to local sense. Otherwise, you will be busy waiting over here if you already enter into there. Until the last one had the local sense to be false, and that's sent to the sense. And then initially, you enter into the next sense area, everybody set to true. And only the local will be reversed to false. And then, because the local is false, and if there's one, the last one arrive, set everybody to be false, then you unlock it, and then everybody move on. And then after everybody move on, you set everybody's sense and local sense to be true. And then you actually will wait until everybody arrive at the local sense, that will unlock it. I mean, arrive at the central barrier and unlock everybody. Non-blocking algorithm, non-lock synchronization. Usually you need to lock if you have a shared memory called X, and you need to lock it and you update it by this function. And we have another way to do it called compare and swap. So in compare and swap, instead of locking the memory X location and update it with lock and unlock, you actually load the X value, calculate the function value, and then return this X value to X. And you have compare and swap. You load the value, you actually calculate the result, and the result doesn't set back to X because it may be a shared copy. So you don't update it, and you do a compare and swap instead. And then that compare swap, if the checking is not true, then we go back to do the same thing again and again. This is called the compare and swap mechanism. Compare and swap is a universal primitive for single location atomic update. A similar primitive known as low-linked store condition is available in MIPS alpha and PowerPC processor. So many processors implement this compare and swap algorithm. Operation on a non-blocking concurrent queue. In the DQ operation, a single compare and swap swing the head pointer to the next node in the queue. So actually, there might be several queues waiting to use that compare and swap. And the in-queue operation on the right, the first compare and swap change the next pointer to the tail node to pointing to the new node, at which point the operation is said to have the logically completed. The subsequent cleanup, compare and swap, which can be performed by any thread, swing the tail pointer to the new red. So actually, this DQ in-queue operations actually just try to make sure that everybody waiting for the condition to be clean, they will be put into a queue until they got the chance to do the compare and swap. So this is one way we manage the mutual exclusion by compare and swap. So memory consistency model, we have this X variable, and this variable shared by core A and core B. So we have the core A that actually update it to before, and then we have core B. So we actually try to maintain the consistency between these two. So for example, we have initially X and Y equals 0. If we update the core A's X equals 1, then we need to set this core B to be to make sure that core B's X is also updated. So we have the write through pass, write back, write embedded method to make sure that. And this X will be A got the access and A update. We need to update X copy in the B core as well. So this is some sort of the write broadcast scheme. And right here, we have discussed this already. Now, I'm going to talk about synchronization part 2, lecture 6, scheduler lock. What is a scheduler lock? Scheduler lock is a lock based on the scheduler. And the scheduler is talking about a thread scheduler or process scheduler. So in the previous lecture, we talked about lock, but those locks are available lock. And right here, we are talking about scheduler lock. And we have one kind of scheduler lock called disable timer scheduler lock, getting the exclusive access to the scheduler. And that is using the disable timer. That's one way to create a scheduler lock. To implement user level thread, OS level processes must synchronize access to the ready list and the condition queues, generally by means of spinning. Code for a simple reentrant thread scheduler appears in a later slide. As in the code, we disable timer signals before entering scheduler code to protect the ready list and the condition queue from a concurrent access by a process and its its own signal handler. Our code assumes a single low-level lock, scheduler lock, that protect the entire scheduler. So what does this mean? Usually a scheduler or scheduler of the process may be will be preempted by a interrupt, or a certain process would have time interrupt, so that your process will be kicked out of the running status. So if we disable the timer signal so that the scheduler doesn't wake up to kick out the existing process for any reason, then we will be able to use that as a scheduler lock to protect the whole process to finish without being interrupted. So that's, we call it the scheduler lock. Before saving its context block on a queue, a thread must acquire scheduler lock, so you will be getting the exclusive access of a certain critical region by having the whole process and having the whole scheduler. But you need to be careful that you don't occupy it really too long so that other people will die. It must then release the lock after returning to reschedule. So right here, we have a pseudocode for part of a simple re-entrant scheduler. So let's look at the EO, for the EO. So if a process that wants to EO its control, then it will disable the signal. That means during this section, from this disable signal to re-enable signal, the processor control will be remaining on current thread. And then we actually acquire scheduler lock and then enqueue the current thread to ready list. That means we remove the current thread from the running status to the ready state. And then we reschedule, pick another new thread. And then we release the scheduler lock and then we enable the signal. So this is the process for EO. So each process has its own copy of current thread. There is a single shared scheduler lock and a single ready list. If processes have dedicated processor, then the low-level lock can be an ordinary spin lock. Otherwise, it can be a spin and EO lock. And for rescheduling, we will have a thread variable or reference, and then we will dequeue from the ready list. Those are waiting for the CPU to process it. Then we find the first one or higher priority one. Then if it is not null, that means we have something that we can transfer the control to. So we exit it and then transfer the control to that process. Otherwise, we will actually release the scheduler lock, and then we acquire the scheduler lock to get another new thread to see if there is a new thread. If there is no new thread, we will just keep requesting for new thread. That is the reschedule. And once we got a new thread, we actually will transfer the control to. And here is a sleep on a certain thread. If it was sleep, excuse me, then we'll enqueue the current thread to the queue. And then we pick another new thread and transfer the control to. So the loop inside the reschedule will busy waiting until the ready list is not empty. So you will pick certain ready list. So it will pick a certain thread from the ready list. The code for sleep on cannot disable timer signal and acquire scheduler lock itself because the caller need to test condition, then block as a single atomic operation. So the reason is that the caller who called it, the thread, may need to test some condition. So that's one way of implementing. And scheduler implementation of synchronization, the code for EO implements synchronization itself because it works as self-contained. The code for sleep on cannot, because the thread must generally check condition and block if necessary as a single atomic operation. But actually, if you need that to have this single atomic operation, then you can have such a code. But usually the code for sleep on cannot, because we need to allow it to check some conditions. And actually that is related to the IO or something. That is the condition we would like to check out. Scheduler implementation of synchronization bounded buffer. Right here is an example of bounded buffer. And bounded buffer actually is easy. The size is limited for the queue or buffer. That's why we call it bounded buffer. And in each time, we have the 2 pointer or 2 index. The input index is pointing to the next available empty spot. And output pointer will point into a certain field spot. So start with by imagining an unbounded infinite buffer, and we have the producer process to write data into the buffer. That is empty slot, and we will consume it and then read it out from output buffer. But once this is unbounded buffer, but for bounded buffer it has limited size, so we just take modular for the index. That will be okay. But there is a certain condition that actually your in and out overlap it. It will either be a empty status or it will be full status. Then you need to make sure that you know which one it is. A bounded buffer is a concurrent queue of limited size into which producer thread insert data and the consumer thread remove data. The buffer serves to even out fluctuation in the relative rate of progress of 2 classes of threads, increasing the system throughput. So basically, buffer, one side may be faster, the other one may be slower. So you keep taking data out at a certain speed, and the other one supplying maybe another speed. And these 2 speeds may not be the same, but with this bounded buffer, we will be able to synchronize it nicely. A correct implementation of a bounded buffer requires both atomicity and the condition synchronization. The former ensures that no thread sees the buffer in an inconsistent state in the middle of some other thread's operation. The latter to force consumers to wait when the buffer is empty and the producer to wait when the buffer is full. Scheduler-based synchronization. The problem with busy wait synchronization, actually that is based on the lock-in variable, and this one is based on the scheduler. So scheduler is not busy waiting, and the lock variable is busy waiting. Is that it consumes processor cycles for the busy waiting synchronization scheme, cycles that are therefore unavailable for other computation. Busy wait synchronization makes sense only if these 2 conditions. First, one had nothing to do. Okay. Second one is the expected wait time is less than the time that would be required to switch context from to some other thread and then to switch back again. So the cost for switching is higher than the busy waiting. Then you would still choose busy waiting. To ensure acceptable performance on a system, most concurrent programming language employ scheduler-based synchronization mechanism, which switch to different threads when the one that are running blocks. So when the other one block, you will be waking up. In the following subsection, we consider some of semaphore, the most common form of scheduler-based synchronization. In lecture about language mechanism, we consider higher level notion of monitor, conditional, critical region, conditional, condition variable, and transaction memory. In each case, scheduler-based synchronization mechanism remove the waiting thread from the scheduler's ready list, returning it only when the awaited condition is true. By contrast, a spin and yield lock is still busy wait mechanism. The currently running process relinquished the processor, but remains on the ready list. It will perform test and set operation every time the lock appears to be free until it is finally succeed. Scheduler-based synchronization is level dependent. It is specific to threads when implemented in the language runtime system, or to processes when implemented in the operation system. So to be short, scheduler-based synchronization is to use the scheduler that actually only one process or one thread will be running on the scheduler. This actually forming the mutual exclusive already, and use that to build semaphore to build different locks and to just make sure that there is a mutual inclusion. And the low-level lock, mutual inclusive lock or variables, that's one way to implement it. And then we have semaphore that is medium level, and we have more complicated monitor, CCR, CV, and the transactional memory. And we are going to talk about this in the later lectures. And in part 3 of this series, we were talking about the semaphore. Part 3 for synchronization, semaphores. Implementing synchronization, semaphore were the first proposed scheduler-based synchronization mechanism and remain widely used. It's very important. Conditional critical regions and monitors came later. Monitors have the highest level semantics, but a few sticky semantic problems. They are also widely used. Synchronization in Java is sort of a hybrid of monitor and conditional critical region. Java 3 will have 2 monitors, and in fact, the current version all have 2 monitors. Shared memory synchronization in 8.95 is yet another hybrid. So right in this lecture, we are going to focus on semaphore, and then we will move on to these different concepts. Implementing synchronization. A semaphore is a special counter. So it's a counter, a synchronized counter, and this counter actually keeps track of the number of seats available for people or for process or thread to enter into a certain critical section. So this counter has the capacity. The capacity C can be actually from 1 to or even 0 to a certain number. That depends on your implementation. And this C has an initial value and 2 operations, P, V, and the changing of these 2 operations will change the value. And this value actually is S. And C is the maximum value that's called capacity. A semaphore keeps track of differences between the number of P and V operations that has occurred. A P process is delayed. The process is descheduled until P minus V less than or equal to C. So that is this condition actually mean there are certain seats available. If you were P minus V less than or equal to the capacity, the initial value of the semaphore, that's the initial value. That actually we call it a semaphore, the capacity. So here we actually has another copy of the scheduling, EO, and sleep. Let's move on to the next page. So semaphore operation for use with scheduler call. So right here we have the implementation for the P function and V function, and it's a synchronized function. And actually this is a Java style function description, and use a mutex so that increment of V and the decrement of P operation on the counter are atomic, and the language structure can ensure it. But actually these 2 are atomic functions. So during the access of these different statements, actually there's only will be atomic. Nobody can break this statement. And this is for P. That's actually a wave function or a consume function, and entrance function. I'm sorry, entrance to the critical section function. And V function is a signal function or exit function. And we have multiple threads that may be trying to get into the critical section, and each one will need to get a semaphore before it can enter into the critical section. So actually there's a certain queue. Those queue will be put in those thread that is waiting for the semaphore. And there is a maximum capacity N a value that it will be set to an initial value, and then initial value is the capacity. And this N is the number of the seat available in a semaphore. So initially right here maybe set it to 6, but when you consume one, that one process or thread enter into the critical section, you should decrease the number of n, that's the available seats, by 1. So this P actually is the entrance to the critical section. We first disable signal, and in the end, we enable the signal. So by doing this, we get the scheduler lock. So scheduler lock in the middle, we make sure this is mutually exclusive. And then if the number of available seats is greater than 0, then we decrease it. Otherwise, we have to sleep until the available queue, ready queue, actually wake this process up to get a lock, get a semaphore. And V is the exit function for the semaphore. Same thing, we have disable and re-enable pair. And in the middle, we have the acquire lock and release lock for scheduler lock. If the queue is non-empty, then we actually can dequeue. So that means there is someone waiting for the semaphore. So we dequeue that waiting one, the highest priority one, put it into the ready queue, ready list, and then we increase the number of the available semaphore by 1. In Java, we have mutual exclusive function, and we use mutex field in every Java object, no separate classes. Every Java object has a monitor, and most one thread may own a monitor at a given time. So two threads, they will be trying to access the mutex. What is the mutex? Mutex is here, this X variable that protected by synchronized function that actually has an atomic function, atomic operation. We call it a mutex. So this X is a mutex. And a thread becomes owner of the object's monitor by executing the object method declared as synchronized. So any instant method described as synchronized, that instant method actually is synchronized on the object. And so that object's data will be actually have the synchronized access. So you cannot update the data without getting this monitor open for you, and that actually form the mutual exclusive access to that object. So here we put an object name over here, reference over here, and this is exactly the same as this function. These two are equivalent. So I prefer this way, so you can call it a synchronized instant method. And once it is synchronized, then your object will be locked up, preventing other people to enter into this function or access the object. Semaphore-based call for bounded buffer. Right here, we have a bounded buffer example, pseudocode. So we have a shared buffer, now everyone can access it. We have next full, net empty. Next full is the out index. Next empty is the in index. So initially we set to 1, 1. And then we have a mutual exclusive control. We call it a semaphore. That initial value is 1. So actually, this is the counter. The maximum capacity is 1. So every time to enter into the bounded buffer, we only allow one guy to get into there. So that's the rule. And we have empty slots and full slot. Empty slot, initially you get it to size. That means everybody are empty. And the full, initially no field slots. So everything is empty. And then the insert function will wait until there is a certain empty slot. If there is no empty slot is actually there is no empty slot, then you cannot insert the data in. But once you have get into the empty slot, then you actually put the data into a certain buffer location, and then we move the next empty to the next possible location by taking the modulus. And we had a mutual exclusive lock to prevent this section to have collision or the inconsistency. And actually, we actually will signal the full slot, means that we have one full slot. So actually, at least the full slot, if there is no data in the remove side, once you fill in something, it will be available to wake up the consumer side to able to actually take out some data. And from this remove function, first we need to check on whether there is a certain full slot or not. If not, then we need to wait on it. And if yes, we go into this function and then we actually take out one data and then we move the next next full or next output variable by taking modulus. And then we actually will be getting out of the function, return the data, and then we will signal the empty slot, means that we actually take out one data so it can continue to insert. If the empty slot is already actually is already full, the size, so not actually no extra data in there. We need to fill some data in. So here are the comparison between mutual exclusive lock and the semaphore. And sometimes mutual exclusive lock can be used to implement semaphore. Mutual exclusive lock somewhat slower than the semaphore. And I believe this is talking about the monitors type of mutual exclusive. And semaphore is generally faster than mutual exclusive lock and require fewer system resources. And only the thread ownership, only one thread can own the mutual exclusive. And because mutual exclusive only allow one to enter into a critical session, while semaphore had a maximum capacity that's specified by initial value. So these are different. Priority inheritance available only with mutual exclusive lock. This feature are now available for semaphore. Mutual exclusion, primary purpose of the mutual exclusive should be used only for mutual exclusive and can be accomplished by the use of binary semaphore, but they may be pitfall. So mutual exclusive for semaphore has pitfall because it actually is not binary semaphore. Sometimes you have ternary or quaternary semaphore that allow more people to get in. So, but there is some pitfall. So, semaphore is not completely used for mutual exclusion. It has different purpose. Inter-thread synchronization do not use mutual exclusive lock for this purpose. And semaphore is better because semaphore is scheduler-based lock. Event notification do not use mutual exclusive for this purpose, and semaphore is okay. So semaphore is more flexible in a way for the application. Thread suspension, thread can be suspend if another thread already owns the mutual exclusive lock. So if you are in the lock, you cannot actually suspend it. And semaphore can suspend its value of counting semaphore is 0. Implementing synchronization. It is generally assumed that semaphore are fair in the sense that processes complete P operation in the same order they started them. Probably semaphore, they are pretty low level, hard to understand sometimes. Their use is scattered over the place, so it's hard to trace back where is the consumer, where is the producer, and where is the entrance section, where is the exit section. It's hard to trace. When used then for mutual exclusion, for example, it is easy to forget P and V is too low level, especially when they don't occur strictly match pair. So actually, if you have strict match pair, it will be easier. But if not, it will be harder to understand which one matched which one, whether we produce enough data or we consume enough data or not, or the number of sales, whether it's considered to be busy or actually is already full. It's hard to trace back. So this concludes our today's section, and we will have the session 2 in the coming a couple of days or maybe tomorrow. So thank you for watching this session 1, and in the session 2 we will be talking about more advanced structures. Thank you. Bye.